Hello, good afternoon. Thank you for attending our DEHN Protects webinar series. We have an exciting session on surge protection and earthing with a focus on practical evaluation of site conditions. I see we have a really strong attendance today, so I really appreciate everybody's time to participate with our June 25th, 2020 webinar series. I'd like to introduce myself. I'm Mark Hendricks, and this is my colleague, Stephen Weber.
Hello, everybody.
Thank you, Stephen. Stephen's running our background coordination. Appreciate everybody's help with this. So today's session is focusing on surge protection and earthing, design, site evaluation. Is it effective and is it complete? So our webinar will introduce the features and benefits that are important in the design and implementation of surge protection and earthing. In detail, we're going to talk about surge protection design, device selection, and site evaluation. In addition, we're going to focus on earthing design, implementation, and site evaluation. So I'd like to just do a quick discussion of the threat environment. We're talking about lightning protection, and so we have a combination of threats, things like direct strike, like the illustration above where it shows the lightning attaching directly to a building. But remember, there's often numerous attachment points that are getting just a little bit of that lightning love, and so you'll often experience surge direct strike effects that are not exactly the primary strike. In addition, there's very common indirect strikes. So this is when it strikes nearby the tree or the ground or even the power lines nearby. They'll produce very strong ground currents, which contribute to ground potential rise. And these effects really are the focus behind our discussion today. So we're looking at the effects of lightning, and so it's always important to pay attention to the pillars of protection. And this is a great illustration that talks about air termination, the down conductor system, and separation distances. Now, these are things that are already installed at your site, and as an operator, you're not really in control so much of those. But on a daily basis, and a normal preventative maintenance program, an operator can inspect and upkeep both their earth termination system and the lightning equipotential bonding. And just to note that SPDs, fall under the IEC 62305-4 recommendations. And again, what's important is that these are the aspects that an operator can maintain, inspect, and upkeep. So I want to start with lightning equipotential bonding. And this is a really great illustration that describes both metal to metal and surge protection. These are the aspects of lightning equipotential bonding. The idea is to create a single potential across your site, across your structure. And the purpose is to prevent differences in potential which will cause ground potential rise to drive currents. And so what's nice about this illustration is it shows things like a metal to metal pipe for gas or for copper water pipes, but it also is a great illustration for things that are not bonded. You have to use surge protection on your telecommunications, on your main AC power, on things like data communication lines. This is where surge protection devices go. And that's where we're going to start our discussions. So I like to always start with the risk analysis. The IEC methods are very helpful because they really drive the risk assessment, which we know is very important for the selection of the rolling sphere radius. And this is a really nice illustration to show you that a less severe risk gives you a larger rolling sphere. A more severe risk gives you a smaller rolling sphere, because that's where we expect small lightning currents, the more higher percentage of lightning currents can be smaller, and they'll actually allow the lightning to get into the nooks and crannies. The smaller lightning currents that we will pay attention to in a more severe category have a smaller striking distance. That smaller step leader can get into the nooks and crannies. And what's nice about this illustration is it shows you the less severe large rolling sphere and the more severe small rolling sphere. But this standard and the risk analysis also gives you great guidance on the selection of SPDs and earthing requirements. So again, the risk drives the mitigation and the selection of protection methods. So why do we care about lightning strikes? Well, things get burned up from lightning. So you have things that are large components on circuit boards, but you can picture that if this is the damage to a large component, what's going to happen to your microprocessors? They don't stand a chance. You have direct fire. We have extensive damage to instrumentation. These are the visible effects of lightning damage that SPDs, surge protection devices, can help mitigate. And what's really important about some of this damage that SPDs can help avoid is it's easy to see when a wire is blown apart, but it's very difficult to find the hidden problems. When a wire is subjected to extensive surge, it may not be visible and obvious, and these are very hard to troubleshoot and find. And this is another reason why the application of surge protection devices is very important before you actually experience surge damage. So you have things that are obvious. You have wires that are burst. Here you can see things like the jacket being torn apart. You have connectors that are completely blown off their circuit boards. You have wires that are exploded. This is really important to help you understand why we're applying surge protection devices. So why are we here? To understand what good and bad practices look like. So an installation in an outdoor public audio amplifier cabinet, we want to look at this because this is a really good example. Position near the point of use, check. It's in the cabinet with the amplifiers. We're using short conductors to connect the wired systems together. Check. You can see it's right in the same cabinet. We avoid tight bend radius. Check. We're using the heaviest gauge that is practical. Check. And we have direct connections to the earthing bar for best control of those voltages. So this is the use of surge protection devices as an equipotential bonding method. So let's look at the application and design and selection. This is a nice illustration of a schematic for a solar power generation plant where we have the actual panels that deliver DC power. Then we have converters, inverters. You have extensive interconnection AC power plant. You also have extensive I/O control areas. You have power over Ethernet controllers. You have power over Ethernet cameras. These are distributed across a large area where you have both earthing and surge protection challenges. And so what's important is to examine your electrical schematics, understand where these devices are distributed across your plant, and apply surge protection devices. You don't want to leave a back door for surge damage to come through a data connection into a very expensive combiner converter on your solar power plant. Another really important aspect to look at is AC panel protection coordination, where you have your main incoming power, where you want to apply a very robust, what's considered a class 1 type protector in the IEC nomenclature. This is able to withstand direct strike energy from ground potential rise and from direct strikes onto the structure. And it's important to coordinate these with downstream AC power protection devices that are near the point of use. And this is often associated with things like transfer switches where you have a backup generator. And you want to make sure that your surge protection devices are as close as possible to the victim equipment. And this is what we mean by coordination. You have an upstream device, you have some distance between the upstream and then the downstream surge protection devices. The standards do a really good job describing the distance to pay attention to. It's generally anything over 10 meters. We'll pay more attention to that in some upcoming slides. But this is what's really important, is to analyze your schematic, understand the voltages that are at your distribution panel. Look for things like transformers where you're stepping down into a lower voltage, where you need to pay attention to separately derived neutrals and additional earthing and bonding. So again, it's about understanding your schematic and selecting the devices that are appropriate at those AC surge panels. So when you're looking at your panel, you're a panel operator and you have these panels across your site, it's important to evaluate your system. And you want to look for things like clean electrical wiring. Check. You can do these inspections literally every day. You can go through your site, you're doing your preventive maintenance. Is it easy to identify your components? Check. Is there a good earth lug in the cabinet? In this illustration, in this photograph, you can see that in the lower right, we do have a good earth lug, but it looks like it's on painted surfaces. So this is something to pay attention to. How good is that bond through a painted surface? But here's a couple of red flags. No SPDs are identified on the AC power. There are no SPDs identified on the low voltage IO control signals. And further, you can see in this upper right image here, there's a missing bond connection to these dead front panels and these doors. And this is important because if there is actually a fault on these electrical systems, that door can remain energized, which is a huge safety concern. And you also have that trouble with equipotential bonding. If it's not bonded and there's a surge, that door essentially sits at a different potential. And now you'll have a voltage, and now you'll have surge currents wanting to flow through the hinge, and you'll get that terrible arky-sparky that is a source of ignition, and it's also a source of damage. Further SPD applications on things like motor vibration and flow meter controls that require protection. Is there surge protection on the AC power? Check. Is there SPDs on the 4 to 20 milliamp right next to the motor control panels? Check. Is there SPDs on the indoor DCS control cabinets, the data control centers? Check. But watch out, there's a red flag. Is there an SPD on these flow meter transmitters that are out at the remote parts of the site? And this is what's important. You need to look at those exposed victims and apply surge protection at the point of use. So central control room protection. This is a really great place to evaluate on a daily basis. You need to look through your facility. You need to analyze, are the computer systems properly protected with AC power and data protection centers? Not only that, you need to pay attention to things like emergency lighting, because this is mandated by National Electric Code and the safety standards that your emergency lighting circuits in these facilities have SPDs applied. And you also want to look at all that incoming line. You don't want to leave a back door into your very sensitive central control room where a surge out at a remote camera can come all the way in and blow out your router. This would be a very critical issue during a lightning storm, right when it's critical and you lose those very sensitive power over Ethernet circuits. So what's important is on a daily basis, the operators can be aware of and look for the areas that need the most protection. Bulletproof protection on both ends. So you've got your exposed IO control and IO flow meters. What's on the other end? Is the cabinet properly protected? CANBUS and power over Ethernet protection should be at every remote control cabinet and in the marshalling cabinets in the control rooms. And I did reference that we're looking for distances, greater than 10 meters, that the IEC standards do a really good job helping direct and offer guidance so that the designers and the operators have an idea of what to look for. Critical inverter and CANBUS protection. These are areas on the plant that are exposed, and you want to look at your cabinets. Is there SPDs on the AC power? Check. Is there SPDs on the 4 to 20 milliamp circuits? Check the box. Are we using short connection wires? Are we using direct connections, good direct connections to the bonding to earth? These are the things that we want to be looking at. And in your preventive maintenance schedule, you can build this directly into your program so that your site is best protected. And here's a really great couple of photographs for grounding, bonding, and protection. These are the things that we're looking for. We're looking for SPDs installed directly on the incoming data lines. Yes, you can see the surge protection device on your IO incoming data. Is it as close as possible to the point of use? Is it proper control of the shield? And this is really a great introduction to that whole topic of shielding. And usually what's considered a best practice is the shield is lifted on the interior cabinet, where the instrument has the shield bonded to the shroud, and on the inside you lift your shield. And the point is to avoid awkward ground loops that will otherwise interfere with your signals. Is there a good earth connection on the cabinet? And you can see that in the bottom of these enclosures, where you'll often see a very sturdy single point ground bar. And here's a nice illustration showing that ground bond on the door, so that door does not present a safety hazard. So these are the things that we're checking for, and we're looking for good practices. Power over Ethernet protection, where you have an RJ45 cable coming from your router. It goes out to extensive equipment scattered around the plant. We're looking for an SPD on that incoming PoE line. We're looking for it to be close to the router, right at the point of use. And we're looking for a good bond directly mounted from the surge protection device onto the earth system, the bonded system of this cabinet. So these are the things that we would put into our maintenance plan and into our inspection list to make sure that we've done it right. And these are the things that the operators can take control of and not fall victim. SPDs on digital control systems. These are extensive systems that have transmitters and instrumentation scattered around a large plant. And here we have SPDs on the incoming 4 to 20 milliamp lines. Check the box. Proper treatment of the shield wires. Is that ground lifted? Is it installed on the other end? Close to the controller, point of use. Is there a good bond of the SPD to the earth? Is there a good single point earth bond inside the cabinet? And here you can see the heavy gauge green wire coming up to give you your cabinet a single earthing bond. And here you can see additional bonding on the cabinet metallic members itself. And everything's coming back to a single earth bond of the cabinet. And this leads back to the single master bond, the ground bar of this particular control room. So these are the things that we're looking for. This is the point of inspection. This can all be part of your preventative maintenance plan. SPDs on flow meters and controllers. Here we can see that the SPD is applied on the remote instrument. Check. SPD is on the incoming 4 to 20 milliamp lines inside of the control cabinet. Is there proper treatment of those shield wires? Is it installed close to the controller point of use? And is there a good bond inside that cabinet? These are the things we're looking for. So this all contributes to what we would call layers of protection, and to create a zone of maximum protection. So you have something like your most exposed point of your AC power distribution coming in. And then you, as it goes downstream into your electrical system, you can see that you can build more and more thorough zones of protection. And this is what we can look at a block diagram level, and then you can inspect your site and see that it was actually implemented correctly. So some helpful hints for selection of SPDs. We get a lot of questions about how do I pick the right SPD for my application? Well, what is your AC voltage? And here we're looking at the nominal system voltage. What is your system configuration? Is it 2-wire, 4-wire? Is it a 3-wire plus ground? Split phase? This is what the questions we have to ask ourselves. What is the AC panel short circuit current rating? So the SPD has to be matched to the breaker that's upstream. You can't have an underrated SPD, otherwise it needs to have a secondary disconnect. What is the SPD surge withstand? Is it truly designed for this application? In this case, we're looking at something that looks like a UL surge type 1, which is a high level of exposure. And where does that SPD actually get installed? Is it inside of the load center? Is it adjacent to it? Is it directly on the DIN rail bus bar? These are the questions that you need to understand so that you can properly select your AC power surge protection. Data surge protection is very similar. What is the signal voltage? 5 volt, 24 volt, 420 milliamp. These are very common applications. How many signal wires? Is this a 2-wire circuit? Is it a 4-wire, perhaps a RS485 circuit? How does the wire connect? Is it a direct punch down block? Is it stripped wires? Is it on an RJ45 connector? What is the SPD surge withstand and protection level? This is important to understand. If the SPD is rated to the surge rating of that type of exposed signal. And then where does that surge protector get installed? Is it on a DIN rail strut? Is it directly at the instrument? These are the questions that you want to ask yourself, and so that when you're looking over your design and when you're evaluating the installation, is it properly selected? So in a summary, what we're trying to do with the surge protection device is to provide equipotential bonding for your electrical circuits at the point of use, so that you have a truly bonded system that contributes to the zones of protection. And that leads us to earthing. And why is this so important? Well, a photograph like this tells you a lot about what's going on in this particular plant. And here you can see something that looks like a quarter 20 nut that's just glowing red cherry hot. So you know that there's a lot of things going wrong here. This is probably indicative of a neutral ground bond that's got too much neutral current flowing, but things like this tell you that there's truly a lot of work to do to evaluate the design and the implementation at a plant like this. So these are the types of things we're looking for. And here you can see this wire is oxidizing from excessive heat. You've got broken connections. These are the things that we're looking for. So earthing design. Remember, it started with the class of protection. So our risk analysis tells us that we have extensive risks, so we select higher protection methods, and this can help us design our earthing system. We evaluate our soil resistivity, and this leads us to a chart similar that we pull from IEC, where we can determine the length of conductors that the earthing system has to have in contact with the soil. So now we can start doing things like selecting a type B or a type A earthing system, and then we can start evaluating the installation itself. So what's nice about the illustrations and photographs on this is it contributes to the design and implementation of your earthing system. And then when the installation is in process, you can inspect for ground loops to make sure that you've got interconnections between the electrodes and the grounding system. So the differences between type A and type B. Type A is considered individual earth electrodes, we can have horizontal conductors, we can have vertical conductors, and this is again driven by what we derive from our risk assessment, which tells us the soil, how to select the earthing, the length of the earthing conductors. Here we have an illustration of the type B ring electrodes, which can be surrounding the building or perhaps embedded within the foundation. And these methods there's combinations that can be employed. So type A earthing electrodes, there's a lot of information available, and basically what we're trying to do is make sure that we've got a proper earthing connection into the soil that you can then come back and inspect at a test joint. Type A earth electrode with a earth rod, and we can see it needs to be buried at least 1/2 meter below the soil. This helps prevent ground potential rise, touch depth voltage issues. It also helps avoid things like frost heave. But again, this goes back to part of the overall design of the system, so that the earthing system meets the expectations and requirements of the design. We've got a few points to make sure. Again, the depth that it's buried. We've got to pay attention to such things as minimizing effects of soil corrosion, frost heat, freezing, and the spacing of the electrode away from the side of the building. And 1/2 meter should be added to the length if you're going horizontal. Earth electrodes with the proven length can be advantageous, of course. So what does this look like when it's being installed? Well, here we have a vertical ground rod being inserted, and we have a conductor being attached. These are the things we're looking for as part of the installation. We're looking for proper connection, exothermic welds, or suitable clamping methods. We're looking for proper treatment of those connections to prevent corrosion over time. These are things that you might see buried with the inspection test well. This is all part of the installation and the design aspect of it. Foundation earth electrodes. We know that we're looking for things like the closed loop. We're looking for the embedded connections so that you have points where you can access that earth electrode. We're looking for connections that are easily identifiable. We're looking for galvanized materials that are resistant to corrosion. A type B earthing electrode system design, you want to make sure that it obeys the recommendations. We're looking for foundations with increased earth contact resistance. So this is what it should look like during the construction phase, where you can see the rebars embedded in the flooring. We're looking for the interconnected mesh. You need to be able to identify these risers that will connect to the building steel at a later time, and this is all part of the design. This is what it looks like during the construction phase. Here we have additional discussions of the exothermic weld connections during the construction phase. You can see the elements in this photograph where they're going into the concrete. We're looking for things like a clean connection. We're looking for PVC protection so that it doesn't come in direct contact with concrete and cause corrosion. And these are the elements that you see in the design, and this is what it should look like during the construction phase. Here we see additional portions of the construction phase. You can analyze your exothermic welds, and you can see this buried mesh that's in the soil before the final layers are laid down. And this is what it should look like during the construction phase, where there may be an opportunity to inspect. And finally, the final system in case of foundations with increased earth contact resistance. We're looking for good interconnection between the dedicated conductors and the rebar that's buried in the actual concrete system. So what does a grounded design mesh system look like at a larger plant? And here we have a large plant with many separate buildings, but the earthing system at a plant like this is going to look like a buried grid. And with a design like this, and knowing the soil conductivity, we can come back and do analysis of touch step voltage. So this is all part of what is the larger design system. And we can take that, and then when it's installed, we can come back and measure the pigtails so that we can see that the intent of the design was met. We can analyze the pigtail connections to each of the structures. You record this into your inspection records, and this can become part of your maintenance records so that every year on a regular basis, you can come back and inspect those connections to make sure that you're not experiencing degradation, or maybe somebody came back and dug it up and interfered with the connection or disrupted your earthing field. And this is the type of information that is useful. You can come back and you can, with Clampon meters that can record the soil, the resistance of the loop, you can come back and analyze a typical structure. And when you see adjacent readings that are very low, like 0.062 or 0.029, then you see an adjacent reading at 19 ohms, you know that something's wrong with that connection. And this is helpful as part of your inspection and troubleshooting, because this tells you what to look for and where to go to find the problem. So in a system like this, a nice illustration like this, you have your inspection records, and then you can come back and find these out of range readings that are the indicator that there's a problem buried or unconnected. So now we've got the systems installed. Now let's look for grounding anomalies. What are the things you're looking for? Here we have some nice photographs showing you've got the application of a small gauge wire that doesn't necessarily meet the standard for bonding this particular fence pole. You've got a single hole lug that can spin loose. You've got oxidation at the lugs. You've got things like the conductor emerging from concrete without treatment that can cause excessive oxidation, and these wires can become brittle and break over time. You've got problems like this where you see severed wire strands and kinks in the wire due to groundkeeping maintenance and things like that. You have broken connections that you're looking for. Here we see the pigtail coming out of the side of the wall, but it's supposed to be bonded to this metal equipment, this metal housing. And here we see it's just laying in the puddle of water. This is the things that you want to watch out for. And this is what an operator can watch for in his maintenance, in their maintenance plans. Corrosion of galvanized steel strip. Now here you see a before and after. The inspector saw this problem and gave it a gentle nudge, and you can see it just severed the connection. So these are the types of things that corrosion over time is going to present huge problems. So this can be dealt with through treatment and proper installation in the first place, use of the proper materials. We're looking for things like general housekeeping. Now here we've got something that looks like just a general mess. You've got splices in the conductors that are difficult to trace. You've got daisy chain operations where you're bouncing through the facility with daisy chain connections instead of having dedicated pigtails coming back to an earth connection. Where's the master ground bar? That would be a better system where everything comes back to one master point. Over here to the right, you see a broken pigtail. These are the things that you can inspect on a regular basis and look for before you have surge and lightning problems. More grounding anomalies. Here we have some photographs showing multiple bonds under one lug with dissimilar wire sizes. So that'll contribute to wires coming loose. Over here to the right, you see that you've got a completely sheared off and broken pigtail connection. You have a single hole bolt where the ring lug completely sheared away. So again, these are the things to inspect and watch for before lightning season comes on. grounding anomalies. Here we've got a single hole lug that can spin loose. You've got oxidation on the lug. It looks like it's probably a casual bond because you've got a wire that's just pressed against a painted surface. Off to the upper right, you can see a broken pigtail connection. These are the things that you're looking for that are going to be signposts that will tell you that you're going to have problems at these areas. And so you might be experiencing instrumentation problems and you're troubleshooting your instruments, and it's not the instrument, it's the earthing and bonding. And that's why it's really important to pay attention to these maintenance issues that you can visually inspect. These are the things that you have control of. We have some more grounding anomalies. Here we have poor treatment where the pigtail emerged from the concrete. It's becoming frayed, it's getting oxidized. Dissimilar wire sizes under one lug where it's going to be difficult for them to maintain proper tension. Off here to the right, you've got a motor stanchion grounding that's not even connected. So it's going to be very difficult to troubleshoot problems with the instrumentation when it's floating bonded. So here we have a direct problem where the instrumentation and the earthing on this motor is going to lead to instrumentation failure because the motor is not bonded. Additional grounding anomalies that are easy to spot. You've got oxidation at this lug. It's possible that it's painted connections, that it's a painted connection. So you're not really getting a good connection in the first place. It's a single hole lug that can spin loose. Although we weren't focusing on down conductors, here you can see in a site inspection that you've got a down conductor coming off the top of a tower, and it's leading into a metal conduit, a steel conduit junction that leads directly into an adjacent structure. So now you're injecting your lightning currents into a steel conduit, which is going to cause massive voltage spikes right here, flashover, and you're injecting your lightning currents directly into a structure, which is the opposite of what you want. You want these down conductors routed away from your earthing system into dedicated down conductors and dedicated pigtails. So what are the things we want to spot as good practice? What should good look like? Well, you've got a pigtail emerging from the concrete. Where it emerges from the soil, it's protected. You've got a gentle bend radius. It's not perfect, but you've got an easy flowing gentle bend radius, which will eliminate a lot of impedance. You've got a clean exothermic weld. You can see the weld has got good contact, and it's been painted and treated to prevent corrosion over time. So these are the things that you want to check for. Additional good earthing practices. It's protected as it emerges from the concrete. It's protected up the side of the wall where it can be damaged by through equipment being moved around a plant, where you want to avoid having your down conductor critically injured over time. You've got gentle bend radius where it goes around corners, and you've got a clean exothermic weld where it attaches to the steel I-beam. So this is the basics of what we covered today. We looked at surge protection design and selection, and we wanted to focus on site evaluation. We looked at earth design principles. We looked at their implementation through the construction phases at a site, and we wanted to evaluate what you see, what's visible on the site that you can actually pay attention to and take preventative measures to protect against lightning and surge damage. So please see us on social media or DEHNUSA.com for more information. We have extensive experience with site inspection services, and we're happy to help. I'd like to open the discussion for questions, if there's any questions from our audience today.
Hi, Mark.
Hi, Stephen.
Yes, we did receive a few questions. The first question was focusing on the risk assessment portion of your presentation that you presented. We always start with the risk assessment. So the person asks, what in the risk assessment indicates the need for a surge protection device? How do I evaluate this need for my facility?
Well, that's a great question, because the risk assessment drives the level of risk for your site. And as part of the risk assessment methods, you have to select mitigation to reduce the risk. So we have extensive conversations that we can take offline. Other presentations that we've done dive into risk assessment in greater detail. But basically what you do is you develop the condition of risk, and then you select measures to reduce the risk. And what you will often find is that you have to apply both a lightning protection system and internal surge protection devices to prevent the risk of fire. And so it's part of a thorough risk evaluation process. DEHN has proprietary software that we've developed that's available, and we could certainly take this offline and go into much greater detail. This is a great topic. Stephen, I'm not sure if you have any other points you'd like to contribute. You personally have done a lot of risk assessment efforts.
No, I agree with you, Mark. A follow-up question is relative to the same aspect. The person asks, in the risk assessment, how does the lighting protection level selection affect the surge protection specification?
Well, this is really a great portion of the IEC methods, because IEC pays a lot of attention to the direct strike energy that's associated with lightning. The NFPA and UL methods, although they're very thorough, they don't have some of the same testing of direct strike lightning energy on SPD devices. So the risk assessment will tell you the measures you need to put in place, and that helps you pick the surge protection device and the energy it needs to withstand. And so this is one of the advantages of IEC methods, is that it allows you to select higher and higher levels of risk to control your risk for things like a hospital with explosive environment, oxygen atmospheres full of people that are very difficult to evacuate, where you have a high risk of fire and a high risk of life threat.
Yes, Mark, I would just like to add that you add or you select a certain lighting protection level in your risk assessment, and that guides you to what SPD you need to select. And you'll notice when you do the risk assessment that if you select a more stringent lighting protection level, say a lighting protection level 3, 2, or 1, that's higher than a lighting protection level 4, you'll notice that the risk keeps on reducing even though you've just implemented the same surge protection measure. And the thing is, there's two factors that really reduce when you select higher lighting protection levels, and that has directly to do with the current carrying capability of the surge protection device, as well as the voltage protection level. So you'll notice from our specification sheets that Mark showed that the current carrying capability, the nominal voltage, the nominal current that the SPD can handle is higher for a selection of LPL 1 or 2 than it is for an LPL 3 or 4, and that reduces the risk even further. So I just wanted to mention that as well, that
Excellent.
Those two factors are exactly what is considered. And remember, the IEC has the assumption, the conservative assumption, that 50% of the lightning current is being distributed into the soil and 50% is being diverted back into the electrical installation. So in other words, if you design a system for LPL3, which is 100 kA lightning strike, the IEC assumes that 50%, 50 kA gets distributed into the soil, while 50 kA might be seen by the surge protection devices. So in other words, you need to make sure for this LPL3 design that you have a surge protection device that can handle a maximum of IN maximum of 50 kA lightning current.
Great.
We have a question about the installation. You mentioned that the shorter the wires are, the better. Could you elaborate on that?
Well, what we're trying to do is control the voltage next to the point of use. So the ideal situation is that you have a surge protector directly adjacent to your computer, and that often looks like that little power strip that you have next to your computer. But at your load center, you want to apply a surge protector directly adjacent to the actual electrical bus bar. And long wires have more impedance. And so what it's doing is it's making the surge protector less effective. A long wire, you're essentially sacrificing the effectiveness of the surge protector. A long wire with small gauge and lots of bends is not as effective to control the voltage. So that's the idea behind a short wire, heavy gauge. And you'll see that in the installation instructions for most surge protection devices. They really do want you to put it as close as possible to the victim so that it's most effective in controlling the voltage.
Yeah, so in other words, what you're saying, if I can just say back, what you're saying is that the voltage protection level that a surge protection device provides for an installation is not just the rating or the across the SPD, but it includes the conductor that's run from the face to the SPD and from the SPD to ground. That's the whole voltage protection level between line and ground that the equipment's going to see. So in other words, the sum of the voltage drop over the top wire from face to SPD, the voltage protection level of the SPD, as well as the voltage drop that you will see from the wire from the SPD to ground, that sum will basically be the final voltage protection level that or voltage that your equipment will see. And that's why keeping those wires as short as possible, or in implementing additional installation techniques like installing the SPD in series rather than parallel, you can reduce those wire lengths to try and get that overall voltage protection level that the terminal equipment sees to be as low as possible. Mark, the questions keep on rolling in.
Excellent.
I'm going to ask you, I just want to find something that is really relevant. So as per the questions you mentioned for selecting power SPDs, we need to match the SPD KA rating with the corresponding circuit breaker KA rating, or with the bus short circuit rating.
So it's the surge, it's the SCR rating, the abnormal short circuit current rating of the breaker that's upstream. So the SPD end it needs to be higher or equal to the breaker that it looks upstream at.
Okay, great. Next question, why is it necessary to bond the door when the door is hanging from a metal?
Well, the metal hinge is essentially a casual contact. And as you'll see it, especially when you have things like lights and instrumentation on that door, if the light socket breaks, you're now injecting fault current into the door, and you don't want to rely on the hinge as your electrical path. That's why you'll see on those doors like a nice metal box, there are studs welded into the door specifically for that jumper wire, and that's why they put them there. We don't want to rely on the hinge. That's a casual connection that's going to oxidize and degrade over time.
Yes.
It might look like metal to metal, but that's not what you want to rely on.
Yes, I'm sorry, Mark. I thought you're done with that question.
Yeah.
How do you test newly built earth pits with a clamp tester when the pits are still isolated to the system?
I'm not sure I understand that question. Can you repeat that again?
He's asking, how do you test newly built earth pits with a clamp tester when the pits are isolated to systems? If I may, Mark, remember, remember we use a clamp tester to measure if there's a conductive loop in the system. In other words, everything is properly connected together. You can use a clamp tester to measure earth resistance of earth rods, but they need to be connected to a larger system so that you have a reduced return path back to the earth rod that you're measuring. The best way to do this is basically to go back to the old-fashioned Follow potential method and try and calculate or try and measure the earth resistance of that earth rod by using the Follow potential method, or to try and find a way in which a return path to that earth rod can be made that is of a very low resistance.
And I might add that when it's unconnected is exactly when you want to do your fall of potential method, because then you're measuring the contact of that rod to the surrounding soil, and you're not obscuring it with the rest of its friends in around it.
Absolutely agree with you.
That's actually ideal time to measure it with fall of potential. And as you mentioned, Stephen, then you can clamp on and make a temporary loop to assure that there's actually a loop around it. So it's a combination of questions, but that's a really good point.
Yes, as you mentioned, severed earth connections can lead to instrumentation problems. What kind of problems are we talking about?
Well, the severed earth connection basically means that you're going to have unequal potential. So if there's a ground potential rise, you'll have the instrument experience a different potential than the controller. And now when there's a change in voltage, there's going to be a current flowing, and the current will flow on your control wires, and it'll then punch through and find a path. And that's the whole point about equipotential bonding. You want everything on the same essential voltage and not force it to find a path through your instrument. And if it's a high enough surge, it will find a path.
Yes, and remember, if you also have grounded control systems, you can have problems with referencing if you have severed grounding connections as well. And like you say, a gap in the equipotential bonding scheme, like you've just mentioned, Mark. Is it necessary to install high voltage devices with surge protection when the utility have provided continuously higher voltage more than 5 minutes?
Yeah, this is a sort of a problem that SPDs do not handle. So it's what's often called abnormal overvoltage. You see things like the loss of neutral, or you see other things where the line voltage is coming in higher than the normal electrical line voltage, and it will overstress an SPD very quickly. SPDs are designed to withstand very short millisecond pulses, not continuous AC sine wave voltage. And so this is something you see where the SPD just completely gets blown off the wall, and the customer might say, hey, the SPD didn't do what it was supposed to do. That is not necessarily a lightning event. That might have been something more like an overvoltage, a continuous overvoltage.
Yes, exactly. Remember, there's a difference between a transient overvoltage, which SPDs are designed to address, and a temporary overvoltage, which is, like you say, Mark, an overvoltage that an SPD really can't handle.
Yeah. Okay.
We have time for one or two. We have time for one or two more questions.
Okay. Well, regardless, any other questions that do come in, we'll definitely address and go back directly with the attendee. I really appreciate everybody's time today. It was great turnout. Thanks again. Everything will be recorded. We'll be posting this on our YouTube channel, and look forward to having our audience attend our future webinar sessions.
I would just like to address this last question
Sure.
Addressing maintenance on SPD, on SPDs. The person is asking, what type of maintenance schedule should he put in place for the surge protection devices he has installed?
So SPDs generally do not last forever. Metal oxide varistors do degrade over time, and it's sort of a double question. How often are you being struck by lightning? How often are you experiencing problems on your site? And so DEHN SPDs offer excellent diagnostic features on the AC power and data products. And what is generally expected is after severe lightning storms, you want to go through your plant and evaluate if your surge protectors have experienced damage. Basically, the DEHN products are designed to release themselves after they've experienced failure, so that they don't sit on the AC power. So after a heavy lightning event, you will want to evaluate your SPDs. In normal maintenance cycles, it's probably once a year is sufficient to go through and look at your SPDs. But again, they don't necessarily last forever. So sometimes I hear things like, well, every 10 years you might want to replace your SPD. And that might work for somebody in a modest climate. If you're in southern Florida, where I'm at, I had heavy thunderstorms just the other day, so I'm paying attention to my surge protection devices every year. So that's it definitely depends on your level of risk that you're willing to absorb, and the type of environment that you're subjected to. Okay. Well, thanks everybody again.
One follow-up question that's relevant to this. Sorry, Mark. Should we all be recommending SPDs with clients with older installations that were once within the scope of the standards for that time, but now do not comply? Should this now form part of a test and inspection?
I would definitely think the answer to this is yes. You want to help your clients come up to the latest sets of standards. Now, that's a very tricky question as well, because it's very difficult to take an old installation and bring it up to the latest,
new standard,
National Electric Code 2020. But the real answer is what's the risk that the client's ready to absorb? Are they okay with their status quo, or are they experiencing problems? So you would,
yes, exactly what I wanted to wanted to add, Mark, is remember, with older installations way back then, we have more robust electronics, more, the PCBs and things back then are less electronically driven. So if a client really doesn't have had a loss or does not really have a significant risk, I would say you could get away from recommending an SPD for that installation. However, if it is a client with sensitive equipment, or a client that has experienced some losses, or a client that is geographically on a hill or in a high risk area, an area with a high ground flash density, I would say recommending SPDs for that type of client would be a important thing to do.
And definitely with older facilities, you want to pay even more attention to the earthing pigtails and inspections of things that are visible, that you can actually track.
Yes, in our experience, that would be a much higher problem. Is that these older installations and older facilities have very weak or damaged grounding connections and grounding grids. So fixing and implementing a proper grounding system would be the first thing to address. Absolutely agree with you, Mark.
Yeah. Yep.
Okay. I'm happy. Thank you, everybody, for joining us today. Please send me some follow-up questions, and we'll send it through to you guys. Thank you so much.
Thanks a lot, everybody. Have a great day. Be safe out there.